Hi, I'm Sivert and I'm a PhD student with the University of Southampton and ARM Research. Today I will present our project on Fused, which is a full system simulator for energy-driven computers. So with the growth of IoT comes an increased demand for ever smaller, lower cost and lower power devices. And as these devices get ever smaller, the amount of energy available for compute is increasingly scarce. Along this line, we move into the field of energy-driven computing, where energy characteristics may be the main consideration during the design process, and where we start asking questions like, how much compute can I do with this power source, rather than how big of a battery do I need for this application. In the extreme end, we might want to get rid of batteries altogether, because they are costly to buy in the first place, and even more so to replace when they eventually expire. In fact, if we wanted to power all of the coming hundreds of billions of IoT devices using lithium coin cell batteries, the Earth would eventually run out of lithium altogether. So instead of using batteries, we will power our devices by harvesting energy from ambient sources, and that can be sources such as solar, RF, motion or wind. Now, energy harvesting and batteryless operation can make for devices that are maintenance free with very long lifetimes at a very low cost. And this is of course very critical for a scalable IoT. There is a problem with energy harvesting though, in that it's an unstable power source. And so a system with little or no energy storage will probably have to shut off quite frequently. One of my main research interests is in a particular kind of energy-driven computing, and that is intermittent computing. And this is where you cope with an unstable power supply by retaining computational progress through power cycles, so that long-running applications can make incremental progress whenever power is available. As I'll show you in the next slides, the operation of these systems is entirely governed by how much energy is available, and so you really have to reason about both the energy and the execution at the same time. In the next slide I will briefly introduce the mechanics of intermittent computing, just to give you an example of what these tight interactions between energy and execution can be like. So the trace on the bottom here represents the power supply of the simple intermittent device as shown above. So from the beginning, the system will wait until the supply voltage has recovered beyond a restore threshold. It will then load all of the volatile data and the CPU registers before the application can continue. Then when power fails again, the CPU registers have to be written back and the SRAM has to be written back to non-volatile memory before the power fails. And of course, it's imperative that the suspend operation will completely finish before the supply voltage drops below the minimal voltage of the microcontroller and the device browns out, in which case you would get a corrupt snapshot. And typically we only have a few micro joules of energy to do this, and so the suspend operation is quite a critical part of these systems. Now, as you can probably imagine from the previous slides, developing and evaluating these energy-driven computers can be quite challenging. And again, the main reason for this is that their operation relies on available energy, and so you have to reason about both your application and the energy source at the same time. Conventional development tools are not really up for the task, because they affect the energy conditions, and they will also lose track if the device under test turns off and on. So in addition to that, the repeatability and the reproducibility of energy harvesters can be quite problematic and difficult to achieve, at least without resolving to very expensive lab equipment. So for our research in energy-driven computing, we needed a tool that could model the complex interactions between energy harvesting, power management and execution, and that's why we started working on Fused. So in this presentation I will start by giving an overview of Fused before moving on to the power modeling methodology that we used. Then I'll present a case study to show you an example of what Fused can be used for. So to achieve our goal of modeling the interactions between energy and execution, we implemented a closed-loop model as illustrated by this diagram. So essentially, the model consists of a feedback loop on the right side, where we feed events and module states from the conventional high-level execution model down to the power model. The power model then computes the instantaneous power consumption and feeds it to the energy storage model, which in turn computes the next supply voltage based on the power supply and the power consumption. The energy storage is usually a capacitor, and a small capacitor in our use case, but it could also be a battery. The power supply would usually be an energy harvester, and so we also included a feedback loop on the left hand side here to model the dependency on the storage voltage. And in this way you can get an accurate IV curve from a small solar panel, for example. So in this work we used a simple intermittent computing platform as the target. A simplified circuit diagram is run on the left side and the resulting Fused model is run on the right side. At a high level, all that the circuit includes is a small capacitor, a voltage detector, and the microcontroller. We've also added a current sense amplifier, and that's just to help us with profiling the power consumption of the microcontroller. We chose the MSP430 microcontroller for this evaluation, simply because it contains on-chip non-volatile FRAM memory, and that makes it very suitable for intermittent computing. We also have an ARM Cortex M0 CPU model available, and we use that for more SoC level research. So we used SystemC for the implementation of Fused, and that's simply so that we can mix and match RTL-like models with high-level transaction level models to really make Fused as flexible as possible while also remaining accurate. We also use SystemC's AMS extensions to model the analog circuitry, such as the energy harvesters and the power management circuits. So now we can run real target binaries on Fused to see how they perform when running intermittently on a given power source and with different power management techniques. In addition to that, we added a GDB server interface so that we can use Fused actively when developing our target applications. And we can even step through the codes and lockstep with the energy environment. And that's something that's very useful when developing these systems, but that you can't really do, or you can't do on the real physical platform. So I'll show you some more details of the power modeling methodology now, before moving on to the case study. So the power model essentially consists of the MCU modules generating module states and events, and that gets sent to a power model via a global event logger. The event counts then get multiplied by event energies, and the power consumption of each module state gets summed up for the current time step. Now to make this work, we need to know the energy consumption of each of the events, and we need to know the power consumption of each of the module states. There are many ways to get these numbers. You can get them from datasheets, for example, but in the next slide we will show you how we obtain them in our situation, where we are using off-the-shelf hardware, commercial off-the-shelf hardware. So to figure out the energy consumption of each event, we took current traces running on the real platform and we synchronized them to an event log from simulation from the same binary. And then we used a non-negative linear regression to find out how much energy we could attribute to each of the events. I should mention here that it's important to have accurate timing to do this, something close to cycle accurate, because otherwise it would be very difficult to figure out how much energy is consumed by each of these events. We were originally planning to use this for these states as well, but we found that it was easier to get the numbers for those from the datasheet or from direct measurements, because the datasheets usually have detailed numbers for the module states, and also direct measurements is fairly simple compared to a regression flow. So Fused can record an arbitrary amount of events during simulation, but not all of the events are actually useful for power modeling. And so to obtain an explainable model and a robust model with a high degree of generality, we chose to use a minimal set of generic features that are based on memory accesses, and we'll explain why in the next slide. But the power model in Fused can be easily expanded and adapted according to the particular needs of the user. So if you wanted to study the impact of specific instructions, for example, you could add a feature for each of the instruction groups or even each instruction. But there is a caveat in that if you add too many features, then power profiling becomes very difficult. And so you might have to resolve to some sort of RTL flow to get the really detailed numbers. In addition to the challenges with modeling the interactions between energy and execution, we expect that most of these energy-driven computers will feature some form of state saving, and so they do need energy-efficient and byte-addressable non-volatile memory. Having tightly integrated NVM, though, can make the power consumption much more variable. So we show that on the trace here, and that's from the MSP430. Which has on-chip non-volatile FRAM memory. So depending on how you access the FRAM and the SRAM in the system, the power consumption varies widely, and in this case it's roughly by a factor of 3. So to reduce the average power consumption, the manufacturer has added a read cache in front of the FRAM, but that further increases the variability in access power, and it makes it more difficult to reason about the power consumption when you're writing your applications. And we do expect this trend to continue, and for this to be the case for future platforms as well, because the main candidates for emerging NVMs, such as MRAM, are more expensive than SRAM to access, and they also have asymmetric read and write energies. For MRAM, for example, it's much more expensive to write to memory than it is to read. And for similar reasons, they may opt to use caches to reduce the average power consumption. And so we do expect that mentally reasoning about the power consumption for these systems will be more and more of a challenge, just because it depends so much on these memory access patterns. So for the MSP, to model the MSP, we chose the 5 features that are shown in the table here. You have FRAM read hits, which are served by the cache directly, and you have FRAM read misses and FRAM writes, which both go to the all the way down to the FRAM cells. And then we have grouped together SRAM reads and writes, and the last category is execution cycles, which we broadly define as a cycle where the CPU is active, but it's not accessing memory. So for the regression and for the testing, we assemble a set of workloads and we compile them with a few different allocation policies to get a large variation in memory access patterns. In total here we have we have 61 binaries. This is definitely too much information for a slide, but in summary, the power model can predict the mean current consumption of a workload to within 4% on average, with a maximum of 23% error. Now again, you can probably get something more accurate than this by using more features or having more insight into the device, but our goal here was to have a simple and explainable model that is appropriate for our use case. Now to tie all of this together, we did a small case study of intermittent computing simulated using Fused, and we compared it to the real hardware. So we ran an AES encryption workload on Fused using a simulated current limited power supply set to 200 microamps. The power supply we used here is close to how a PV cell works, but it's much more suitable for use in the lab when we're comparing simulation results to real hardware. The reason being the repeatability and the reproducibility issues with real energy harvesters that I mentioned in the beginning. On the bottom of the graph here, you have the stored voltage on the capacitor shown in orange, and you have the supply to the microcontroller that's shown in light blue, and then you have the current consumption of the system in black. And on the top you have the I/O signals, and they indicate what the target application is doing. So when it's restoring state, when the CPU is, when the application is active, and when it's suspending state, and also when an iteration of the workload starts. So as you might reason from this graph, intermittent computing can be quite an extreme case of energy-driven computing, simply because of just how dependent the execution is on available energy, and also vice versa. So in this example it takes about 70 power cycles to finish a single iteration of the workload. And of course the application completion time is very sensitive to the supplied power, and so that's something we wanted to explore a bit further. So we did repeat the experiment with different supply currents, and we compared the resulting workload completion times against real hardware on a real development board, and we found that it matched to within 6%. So this shows that with Fused we can accurately determine how long an application takes to complete while running intermittently on a given power supply. So to summarize, Fused is our solution to modeling the tight interactions between energy and execution that you find typically in energy-driven computers. We do this by modeling energy and execution in a closed feedback loop, and we use high-level event and state-based power modeling to do that. Fused runs unmodified target binaries, and it allows experimenting with a large variety of energy sources, energy storage and power management. And we have released the source code for Fused openly on GitHub, together with some usage instructions, so you can download and you can try it out for yourself fairly easily. As a last note, I would like to mention some future plans for Fused, as it is an ongoing project, and I do encourage anyone who is interested to have a look at the repository, and of course I invite contributions to the project. So we're currently working on making it easier to do more higher level or PCB level modeling with Fused by adding a board abstraction. Hopefully this will also be useful for the next step, where we want to look into using Fused for wireless sensor network simulation, where each of the nodes are intermittently powered. We also are working on implementing a few reference energy harvesting modules, again to make it easier for you to check how both your target application and power management and so on will work with different energy harvesting types. If you would like to contact me for any questions or support regarding Fused, my email is here on the bottom, so feel free to contact me there. In any case, thank you for watching this presentation, and I'm looking forward to hearing your questions afterwards. Thank you.